All right, just a few short things before we get started with class material. So I was asked to share this information with you today from AMSA. So there's a meeting tonight in social work. So if you have any interest in that, please check it out in the notes. And then a couple things I wanted to bring up before we start are this Thursday's office hours are a little bit different, not too much different, but I'm going to push them back by a half hour. So it'll be 12 to 1 p.m. instead of 11:30 to 12:30 as they normally are. So just be aware of that if you're planning to come. So a little bit limited Thursday, but I'll be there for that time. And then the other thing that's happening very soon, I think it starts tomorrow, either tomorrow or Thursday, I forget the exact date that they open up, is the online course evaluations. So they'll be opened up and available through May 2nd. So there's, of course, an open debate about how much they matter, but they do matter at least a little bit, so we appreciate if you take the time to do those anytime between now and May 2nd when the last day of class is. All right, so that's going to happen, and I'll try to remind you about that once or twice more before the end of the semester to make sure as many people do it as possible. All right, so let's get into what we're going to talk about today. So the first thing we have is just to go over how the last exam went, which I'm sure some of you are trying to forget, but we're going to bring it up just briefly at the beginning. So the average this time was about 2.4 points out of 20 lower than the first exam, and that's actually pretty typical. And believe it or not, this is not the worst it's been. So our average was 11.4 out of 20, which is 57%, with a wider distribution this time. So we definitely see that on the second exam, a wider distribution of scores. That was actually a bit better than the last time I taught this course in a non-pandemic semester. So that was spring 2019. We did a little bit better than that, and basically the same as the year before that. So these scores are pretty consistent with historical averages. And this time there were 2 students out of roughly 120 of you that got perfect scores. But as you can see, there was a range of everything else in between. All right, so we've talked about this already with many of you individually. So if you're, if you're not happy with how the second exam went, keep in mind it's just one exam. There's still another one and a final to go, so a lot more opportunity to improve your grade. You're just going to have to change your habits and come talk to me about the best way to do that. So we have, we're in the home stretch now, roughly a month or so left before this all wraps up, but still a lot of chance for your grade to improve if you were not too thrilled with how the second exam went. All right, so you can take a look at that if you want to see how you did compared to the rest. But as you can see, there was a wide range of pretty much every score possible. So, all right, so what we're going to get into today with the course material is continuing our discussion of ideal gases. Now, we haven't really discussed what exactly it means to be an ideal gas. We're going to get to that in more detail next time. But essentially, for our purposes, an ideal gas is one that follows what we're about to introduce, which is the ideal gas law. Now, that's an unsatisfying definition, but basically, on Earth, at room, normal temperatures, normal pressures, with typical gas molecules that are small molecules like oxygen, nitrogen, things that are in our air, those gases will behave like ideal gases, which means they're going to follow this ideal gas law that I'm about to introduce. So what we did last time was we learned about 3 proportion relationships for the volume of a gas. So how the volume of the gas responds to pressure, how it responds to temperature, how it responds to number of moles. And so those are named after 3 different people. So we have Boyle's law that we talked about last time, which is the relationship between volume and pressure. And we saw that those 2 are inversely related. So when the volume goes up, pressure goes down, and vice versa, all else being constant. We then talked about Charles's law, which involves temperature. So from a conceptual standpoint, you should know what these different laws are. But as I'll show you, there's only really one equation we need to know that puts all of these together. So Charles's law is that the volume and the temperature are directly related to each other. So when the temperature of the gas was cooled, the gas shrunk, the volume compressed, and then vice versa when the gas is warmed up. And then Avogadro's law, which is perhaps the most sort of intuitive of the 3, which is that volume and number of moles are proportional. So the more gas you have, the larger volume it takes up if the pressure and temperature are held constant. So these are 3 individual gas laws, and like I said, you need to know what the 3 of them are, and there are equations associated with each of these as well that we derive, the P1 V1 equals P2 V2 and so on. But as I'll say, from a mathematical standpoint, we're going to put all these together, and this is really the only form you'll need to know is the combined gas law. So when we have 3 proportionalities, so volume is proportional to 3 things. It's proportional to 1 over the pressure, it's proportional to the temperature, and it's proportional to the number of moles. In math, what you can do is if you have something that's proportional to three things, you can combine them by taking the product of those three things. So if volume is proportional to all three of those quantities individually, it's also going to be proportional to the product of those three things. That's just a mathematical trick. So then we can write it like this. We can say that volume is proportional to 1 over the pressure times the temperature, which comes from Charles' law, times number of moles, which comes from Avogadro's law. So volume is proportional to the product of these three things for any gas. And then we can rearrange this a little bit. Let's get rid of the fraction of the denominator and just cross multiply to rearrange and write that pressure times volume. So we're going to multiply both sides of this by pressure. That's going to be proportional to the number of moles times the temperature. All right? And as we talked about last time in the context of all three of these individual gas laws, if you have a proportionality and you want to make it an equal sign, you just have to put a constant on one side. And the constant we're going to involve in this one is called R, capital R, and we're going to put it on the right side of the equation. So pressure times volume is going to be equal to N times a constant R times T. This is the more familiar form of it, PV equals nRT, which you may have already heard of before. Now in this equation, this is very useful because this is what we call an equation of state. Basically, pressure, volume, number of moles, and temperature, those are the only four things you need to know about any gas to be able to define everything else about it. So you don't need any other variables in this equation. So R is a universal constant. It applies to every gas, every ideal gas in the world. And so it's always going to be equal to this, and it's on your periodic table, so you don't necessarily have to memorize it, but it's another one of those constants that we'll use over and over again, so you probably will. So it's 0.0821, and those units that are most commonly used are liter atmospheres per Kelvin times number of moles. All right, so again, N is number of moles, of course that's in moles. T is absolute temperature, so it has to be in Kelvin, and this is the constant that you would produce when you're using liters for volume and atmospheres for pressure, which are the two most common volume and pressure units for gases that we'll encounter. So this R here is called the universal gas constant, and as I said, it's the same constant for every ideal gas. It doesn't matter what the gas is, and so this equation always applies, and there's only one value of R that you need to worry about when using this equation. So this is called the ideal gas equation here, PV equals nRT. And you don't necessarily, as we'll show you when we go through this, you don't necessarily need to know these three individual equations, or you don't need to necessarily know any other combination of two of these variables, because we can always derive the relationship we're looking for starting with PV equals nRT. So as long as you know PV equals nRT, from a mathematical standpoint for solving a numerical problem involving ideal gases, you'll always be able to figure out what equation you need, what the relationship is between the units that you're considering. Okay, so that's the ideal gas law, which is a combination of the three we talked about last time, and now it has this universal gas constant R as part of it. Okay, so using PV equals nRT, we're going to go through now just a bunch of different problem types that sort of illustrate how we can use this equation. All right. So this one here is a fairly straightforward one where we're using this equation, and so what we have is a 0.1 mole sample of neon gas, which would be used in neon lighting, as the name implies, and it occupies a volume of 2,503 milliliters and exerts a pressure of 551 torr. What is the temperature of the gas? So this is a problem where we have three of these four variables defined for us. We have the number of moles of the gas, we have the volume, albeit in not quite the right unit, and we have the pressure, again, when we change units, but we have pressure, volume, number of moles, and we're just trying to figure out what would the temperature of this sample of gas be. So this is a situation where we're using PV equals nRT, and we're just solving for whatever's unknown. So that's one way we would approach this. This is not the most common type of problem we'll see, but it is one of them. So in this case, we're just solving for temperature, so we just rearrange PV equals nRT and say that temperature is pressure times volume divided by N times R. Now, when we're doing this, though, whenever the universal gas constant R is part of the calculation, we have to make sure we're using the correct units for pressure and volume. And as we said, the typical value for R that we're going to use is 0.0821 with units of liter atmospheres per K mole. So again, volume has to be in liters and pressure has to be in atmospheres if we're going to do a calculation that involves R as part of it. All right, so we have some conversions to do before we can start plugging numbers in. So we need our pressure to be in atmospheres. and it's not given to us in that way. So this is where those pressure conversions come into play that we talked about. So here we have a pressure of 551 torr, and the common conversion factor that we introduced last time was that 1 atmosphere is equivalent to 760 torr. Torr and millimeter of mercury are, as we said, the same, just named differently. And so we need to convert into atmospheres, so we get 0.725 for the pressure in the correct units of atmospheres. And then our volume needs to be in liters. This one's a little bit easier of a conversion because it's just milliliters. But again, we're told that the volume is 2,503 milliliters. And we have to convert that to liters by dividing by 1,000. All right, so it's important whenever using R, the universal gas constant, in a calculation, that pressure be in atmospheres and volume be in liters. And so now we have everything we need to be able to solve the problem. So we're going to put pressure as 0.725 atmospheres, volume as 2.503 liters, and then in the denominator we have number of moles. That, of course, is just going to be in moles, which here was directly given to us. And then R, the universal gas constant, 0.0821 liter atmospheres per k mole. All right, so atmospheres cancel out, liters cancel out, moles cancel out. We have 1 over Kelvin, so the final answer will be in Kelvin, which is going to be 221. So this would be pretty cold. If we want to do it in Celsius, we subtract 273, so it'd be minus 52. I didn't specify units here, but we should know how to convert between Kelvin and Celsius. So the initial temperature we get is the absolute temperature in Kelvin. Converting to Celsius requires us to subtract 273, so it's a very cold temperature, not one we would likely experience on planet Earth. All right, so or at least at the SC level. All right, any questions on this one? So this is just using the ideal gas equation, solving for an unknown. It's a fairly straightforward application of that equation. Any questions on that? Okay, so the next thing we're going to do is we're going to talk about some more typical problems we'll see where we have some of those quantities, pressure, volume, number of moles, temperature, some combination of those 4 quantities is going to be changing during the problem. We're trying to figure out how does the other one change in response to that. And so we had problems like this last time for those individual gas laws, Boyle's, Charles, and Avogadro's. Now we're going to see how that works in the context of the ideal gas law, which combines all 4 of those into one equation. So here we have a balloon with a volume of 255 milliliters, which is initially at 912 torr and 25 degrees Celsius. We let it up into the sky, and it goes to the higher point of the atmosphere where the temperature and pressure are now minus 23 Celsius and to 2.28 torr. So it goes pretty high up where the temperature and pressure are much lower. We want to know what is the volume of the balloon under these conditions. So this does not fall under any of the individual gas laws because 2 things are changing. The pressure is changing from 912 to 2.28, the temperature is changing from 25 to minus 23, and we're asking how the volume is changing in response to that. So we don't have a single Boyle's law, Charles' law, Avogadro's law that covers that because it's 2 different variables changing. So for this, and for any type of gas law problem now, we can start with PV equals nRT and derive the relationship that we need for those changing units. Okay, so when we're doing these types of problems, we want to look at the problem first and identify which of these quantities are constant. Now, R is always a constant, it's the universal gas constant, but are any of the pressure, volume, number of moles, and temperature going to be constant in this? So you look at the problem and you see, does it explicitly say that they're constant, or does it not say anything at all about them? And the one that it doesn't say anything at all about is the number of moles. So it's a balloon, so assuming our balloon is not leaking, the amount of gas inside the balloon is going to stay the same. So we are going to assume in this problem that number of moles is constant because it's a closed container, in this case a balloon. And typically in problems like this, if you're not told anything about one of the units, if you're not told what its quantity is at the beginning or the end, or you're not trying to solve for it explicitly, then you will assume that it's constant. Here again, number of moles, we don't really say anything about it at all in the problem, so we assume that it's constant. It is a closed container, a balloon, so we would expect it to stay constant as long as there's not a leak of some sort. So then what we're going to do, once we identify what the constants are, which are always going to be R and possibly 1 or more of those 4 quantities in the equation, then we're going to move everything that's constant to one side of the equation. So in this problem, as we said, N is constant, R is always constant, so we're going to move those to one side, and we're going to rewrite this as PV over T equals N times R. So that ratio of pressure volume over temperature equals two constants in this problem, N and R. And as we said last time, when you have a set of variables, some sort of product or ratio of variables set equal to a constant, what you can do is you can say the initial and final conditions involving those variables have to equal each other, because that quantity, PV over T, is remaining constant through the whole thing. So what you can say then is that P1 V1 over T1 equals P2 V2 over T2. So this is a combined gas law, which technically speaking it combines Boyle's law and Charles' law together, but again you don't need to know that because you can just get it from PV equals nRT. Everything that's not constant we group together, pressure, volume, and temperature, but because that ratio is equal to a set of constants, N times R in this case, then the initial and final conditions, P1 V1 over T1, is going to be equal to P2 V2 over T2. Those have to stay the same. So we've derived a new equation that applies to this specific problem. I mean, this would apply to any problem where pressure, volume, and temperature are changing, but I think for each individual problem, it's helpful to just not memorize all the different possibilities, but to always derive it from PV equals nRT. So what we're looking for here is the final volume, which we'll call V2. So we're going to solve this for V2. So we have to do some cross multiplying and dividing, but what we get is P1 V1 T2. So we cross multiply it by T2, and then on the other side we're going to have P2 and T1. So I like to sort of group the quantities together like that, but however you choose to do it, that's going to be it. P1 V1 T2 over T1 P2. So a little bit of algebra to get that, or you could just start putting numbers in first and solving however you prefer to do it. And now from here we can go forward and start putting in the quantities that we need. So in this type of problem, we've dropped out R from the equation because R is a constant and we moved it out in this case. So we don't necessarily need to have pressure in atmospheres and volume in liters. Temperature always has to be in Kelvin. That's non-negotiable for any gas law problem. But in this case, since we're not using R in this calculation, it's only a function of pressure, volume, and temperature. Pressure and volume can be whatever units they want to be as long as they're consistent. So P1 and P2 have to be the same unit so that the pressure units divide out, and then V can be whatever unit we choose for volume that's given to us. So in this case, we don't have to do very many or any unit conversions, we just have to convert the temperature. All right, and so what we're going to have then is P1 is going to be 912 torr, that's the initial pressure. V1 is the initial volume, which, as I said, we can put whatever unit we want in. 255 milliliters is how it's given. And then we do have to convert the temperatures, though. So T1 here is 25 Celsius, which is 298 Kelvin. 25 plus 273. T2 is going to be minus 23 degrees Celsius plus 273 is 250 Kelvin. So we have to make sure we get those into Kelvin. That's the only conversion we need. So T2 is on top, so it's 250 Kelvin. And then in the denominator, we have the final pressure, which is 2.28 torr, and the final temperature, which is, the initial temperature, T1, which is 298 Kelvin. So we have to make sure we put everything in the right order. That's the trick here. So we get a very large number, 85,570 milliliters. Our answer choices are in liters, so we have to divide that by 1,000 and we get 85.6 liters. Now this would have to be some impressive elastic material to be able to expand from 255 milliliters to 85 liters. 85 liters would probably be roughly the size of, I don't know, I mean, it'd be like a huge thing, right? So there's probably no balloon in the world that could expand that much without popping, but nonetheless, this is not reality, this is chemistry, and the answer would be A, which is 85.6 liters.
In chemistry, there are going to be lots of theoretical things, like theoretical means like in terms of theory.
Yep, there's a lot of theoretical things, and we just like to mess with you guys, so that's all part of it too.
How come in some subjects there's theoretical things?
Well, this is a theoretical course. You'll learn the practical things in the lab course, and here we're just trying to teach you the theory behind it, so that's kind of the idea there. So 85.6 liters, but if you trust the math works out, and that's one of the answer choices, so don't think too hard about reality. Now, of course, the one answer choice you can always eliminate is the one that's negative. You can't have a negative volume, right? So that's where, again, if you had put the temperatures in Celsius, one of those would be negative, and you come out with a negative answer, that should immediately tell you that something is wrong. You can't have, none of these can be negative. Pressure, volume, number of moles, temperature, all have to be 0 or above. I mean, you can't have anything less than 0 for any of those quantities when you're on an absolute temperature scale, which we are for this equation. Okay, so we could have eliminated that answer without even thinking about it. The other three we have to work out the problem to get, and it comes out to 85.6. So any questions on that one? All right, so let's move on to another one. Again, it's a similar type of problem. So here we have, this time, a gas cylinder with a fixed volume. So the volume is constant. That's what fixed volume means. So again, when we're doing problems like this, it's helpful to identify which units are constant, because those don't need to be included necessarily. So the volume is constant and is filled with 239 moles of hydrogen and has a pressure of 136 atmospheres. If we remove 176 moles, what is going to be the new pressure? All right, so again, in problems like this, no matter which situation you're considering, the way I'll always show you how to do it is starting with the ideal gas equation, PV equals nRT. And then we have to identify which of those quantities is constant. So in this problem, we're not told anything about temperature. So again, if we don't tell you anything about it, you have to assume it's constant. There's no way to account for it. So temperature is constant. Fixed volume, as we said, means that volume is constant. And in any problem, R is a constant. So those are the three that are constant in this case. And what we're changing is number of moles and pressure. So we had a relationship last time between volume and number of moles. This time we're going to derive a relationship that involves pressure and number of moles, which, as I said, you don't have to memorize that because we can always get it from PV equals nRT. So those three are constant, and as we said, what we're going to do then is we're going to move the constants over to one side of the equal sign. So we're going to divide both sides by n and divide both sides by v, so we're going to get pressure divided by n. Those are the two that are changing in this problem, is equal to RT over V. Those are the three that are constant. So you have to do a little bit of algebra to rearrange the equation correctly, but once we do that, then we know, because this ratio P over N is constant, we can then write the way that we've been doing now, which is P1 over N1 equals P2 over N2. And this one, as far as I know, is not a named gas law, but it is a simple one that involves just two quantities. And we're going to solve now. We're looking for the new pressure at the end of this, so it's going to be P2, which is just P1 times N2 over N1. Now, what we have to be a little bit careful about here is the initial number of moles is given to us here directly. That's N1. But then for the final moles, N2, we're telling you here how many moles are removed. Remember, the N2 is going to be how many moles are left at the end, how many moles are still present in the cylinder. So N2 is going to be the amount that we started with minus the amount that we're removing, which is 176. So in these equations, the number of moles is how many moles of gas you actually have, not how many you've gotten rid of. So we're starting with 239 moles. We're removing 176. And so that means there's 63 left. That's going to be our N2 quantity. So now we're ready to put everything in. So the initial pressure is 136 atmospheres. N2, which is the final number of moles we just figured out, is 63. And then N1, which is the initial number of moles we told you directly, is 239. Moles cancel out, and that gives us a pressure in atmospheres, which is 36 atmospheres. All right, and as I said, this is another relationship, pressure number of moles, that we didn't directly introduce, and I'm not even sure if it's named after anybody or not, but it's one that we can get starting with PV equals nRT, and that's what we would do for this type of problem. All right, any questions on that? Okay, so those are just a couple examples of how we use the ideal gas law in different types of quantitative situations. Again, either solving for an unknown, or more commonly, like we did these last two problems, rearranging the equation for an initial and final set of conditions. Now, the other thing we're going to talk about that's closely related to this is how to calculate the density of a gas, which is just going to be a slight rewriting of the ideal gas law to get density of a gas. All right, so starting with PV equals nRT. Now, remember that. What is the definition of density? Anybody remember? Density is a ratio of two quantities. What two quantities is it a ratio of? Mass and volume, okay? Now, ideal gas law does not have mass in it, but it does have volume. But we should know from things that we started talking about back in chapter 5 that number of moles is closely related to the mass of the gas, right? So number of moles, it can be written as the mass of whatever gas we have divided by its molecular weight or molar mass. Okay, so that's just another way of writing number of moles. So what we're going to do is we're going to make that substitution where M is the mass in grams and MW is molecular weight or molar mass. All right, so that's a relationship we used all the time in chapter 5. We're going to use it again here. So we're going to replace N with this ratio here, mass divided by molar mass. And so then we have PV is equal to mass divided by molar mass times RT. And then as we said, density is mass over volume, so we just need to solve for that. So we're going to move volume over to one side and move everything else over to the other side. And what it comes out to, after we do the correct algebra, is mass over volume is going to be pressure times molar mass divided by RT. All right, so this is an equation for the density of a gas. So in this case, it does depend on the identity of the gas. So the ideal gas equation, PV equals nRT. If you're working in number of moles, you don't care what gas it is. Any ideal gas will work for this. Now when we solve for density, it is dependent on the molecular weight, which of course is determined by the identity of the gas. So, two gases that are at the same temperature and pressure would have different densities if they're different gases, different molar masses. So that's what this equation tells us. Okay, so that's an equation involving molar mass, and now we rewrite PV equals nRT in terms of that and gives us a relationship for density. So again, for this, there's really two ways you'll use this relationship. So one would be, the problem I'm going to do is a pretty straightforward one where you're just calculating the density of a gas. Now the other problem type that's going to be common is going to be solving for the molecular weight of an unknown gas. So if you measure the density of a gas and you know its pressure and temperature, you can solve for molar mass. We've had a few problems now, mainly in chapters 5 and 6, where we ask you to identify a substance by determining its molar mass, and now we have another way of doing that for gases. So be prepared for that, but again, it's just going to be involving rearranging this equation and solving for molar mass where the density is going to be given to you. All right, so let's just see how we use this equation then for ammonia. So ammonia is NH3, and we want to know what is the density if it has a pressure of 500 in torr and a temperature of 37 Celsius, which is a hot summer day in Houston, about 98 Fahrenheit. So let's see the density under those conditions. So we're going to use that equation we just derived, which you could memorize it, or you can always derive it since it's a pretty simple derivation. Pressure times molar mass over RT. And now we just have to put things in. But again, this is a situation where when we're using this equation, we're using the constant R, so we have to make sure everything is in the right units. So pressure in this case needs to be in atmospheres. So we're given pressure in torr, so we have to divide that by 760 to put it in atmospheres like we did before. So gas law problems are typically not too difficult, but a lot of people get tripped up on units. You have to be careful with units, which I've been harping all semester and becomes especially important in this chapter where we have different units involved sometimes for pressure and volume and things like that. So we're going to use that as our pressure in atmosphere, and then we need the molar mass of the gas as well. So we've done a molar masses ad nauseum in the last couple chapters, so it's going to be nitrogen and 3 hydrogens, NH3. So we have an atomic mass of 14.01 for nitrogen, that's off the periodic table. Hydrogen is 1.01, and there's 3 of them in the formula. And so the sum of all of those is 17.03 grams per mole. And then the temperature always has to be in Kelvin for any type of gas problem, so we have to make sure we do that as well. 37 degrees Celsius, add 273 to make it 310 Kelvin. All right, so we did have some unit conversions to do here, and we had to calculate molar mass before we could get started, but now with all those numbers, we just have to plug them in and we're good to go. So pressure we had to put in atmosphere, 0.658. And then molar mass we calculated was 17.03 grams per mole. and then 0.0821 is R, and then the temperature in Kelvin is 310. So what that comes out to is 0.440, and again we have to be careful with units here. So atmospheres cancels, moles cancels, Kelvin cancels. What we're left with is grams per liter. So that's the unit we're going to get out for density when we calculate it in this way. Now you might be saying that, oh, well that doesn't sound so low, right? Water is a density of 1, this is a density of 0.44, that's not that different, but this is a totally different unit. Water is 1 gram per milliliter, this is 0.44 grams per liter. So typical gas, this is a reasonable pressure, close to atmospheric, or at least 65% of atmospheric pressure, temperature on a hot day. The gas density is going to be usually about 1,000 times smaller than a typical liquid. So water is a density of 1 gram per milliliter. Most gases are going to be densities on the order of grams per liter, so about 1,000 times smaller. And we talked about how gas molecules, what distinguishes them from liquids is how far apart the atoms and molecules are from each other, and that leads to a much lower density, which we can calculate in this way. And if we're paying close attention to units, we'll realize this is a much smaller density than you would get for a typical liquid. All right, I don't think there's probably any liquids in the world that would have a density this small. All right, any questions on that? All right, so that's our application involving density. Now the next thing we're going to go into, which you guys are going to love, is how to use the ideal gas equation in the context of stoichiometry. Come on, you don't have to look that disappointed. So this is the topic that will never die, although I believe this is the last time that stoichiometry comes up. Chapter 9 doesn't have any, so last time stoichiometry comes up. And we're going to use the ideal gas law in concert with concepts involving stoichiometry to be able to relate number of moles to, again, pressure, volume, and things like that. So let's review all the different ways we have of calculating moles. This is going to be the fourth one now that we have, and we're going to need to know how to use all of them in the different ways they come up. So if we talk about the number of particles, number of atoms, number of molecules, things like that, the number of moles n is the number of entities or particles that we have, whatever we're counting, atoms, molecules, ions, so on, divided by Avogadro's number. So that was sort of the definition of a mole that we first introduced. We don't use it as much in stoichiometry, but it is the definition of a mole and one relationship with that. The most common ones we saw were the next two in chapters 5 and 6. The relationship between mass and mole, the one that we just sort of reviewed today in the context of gas density, which is that the number of moles is the mass in grams divided by the molar mass in grams per mole. So that's one that we used a lot in chapter 5. Chapter 6, we talked about moles in solution, where we said that the number of moles is equal to the molarity times the volume, capital M being molarity, moles per liter. So for reactions that happen in solution, we use this relationship a lot to find the number of moles of a solute that was dissolved in the solution. And then finally, now that we're in the gas phase, talking about ideal gases, we have the ideal gas equation. And number of moles, which is abbreviated as N, is going to be PV over RT. So what's helpful to realize, I don't know if I have a problem exactly like this in today's lecture, but you'll see some on the homework assignments. Number of moles is directly proportional to pressure and volume, right? So if you look at this equation rearranged for number of moles, the higher the pressure, the more number of moles you have. The higher the volume, the more number of moles you have. And so what that means, when we're talking about stoichiometry problems, let's say we have a gas phase reaction. So all the reactants and products are gases. A gas plus 2B gas going to 3C gas. We talked about how in chapter 5, when we first introduced stoichiometry, we interpret this as 1 mole of A reacts with 2 moles of B to give you 3 moles of C. But because in a gas situation, number of moles is proportional to pressure and volume, the mole ratios are equivalent to the ratios of the pressures of the gas that react or to the volumes of the gas that react. So for an ideal gas, we could read this chemical equation as 1 atmosphere of A reacts with 2 atmospheres of B to form 3 atmospheres of C, provided that the volume and the temperature are constant. Or alternatively, which is even more useful, we could say that if we have a constant pressure and a constant temperature, N is proportional to volume, so we could say that 1 liter of A reacts with 2 liters of B to form 3 liters of C. So they react in that same ratio in terms of volume as well, because N, number of moles, and volume are directly proportional to each other, so the mole ratios and the volume ratios are the same. Now that only works for ideal gases. These relationships only apply to a situation when all the reactions and products are gases, but that's going to be a concept that's going to come up in some of the problems we do. Now, I think today we're not going to use that exact same concept, but we're going to talk about sort of another way that we can use PV equals nRT in the context of stoichiometry. And so let's go through that here as a pretty drawn out example with a few different steps. Now the first one here is a little bit different, but again, it relies on that same idea that we just introduced. So if we have N2 and F2 reacting to form NF3, so the equation is given here, and they're combined in a 1 to 3 mole ratio at a total pressure of 1.25 atmosphere, and that forms NF3 quantitatively. So again, these react in a 1 to 3 ratio, so if we combine them in a 1 to 3 ratio, that's what we're going to get. If the reaction is carried out at a constant temperature and volume, what is the final pressure at the end of the reaction? So what we're going to do here is we're going to again use the relationship between pressure and number of moles, because what we're saying is we're starting a reaction with N2 and F2 in a 1 to 3 mole ratio. So we can basically assume that we have 1 mole of N2 and 3 moles of F2 to start. And then they're going to react, and when they react, at the end of the reaction, we're going to have 2 moles of NF3. So they combine a 1 to 3 ratio, and the coefficients tell us that if 1 mole of this reacts with 3 moles of that, we get 2 moles of the product. And so what we're asking here is, we want to know what's the final pressure at the end of the reaction. So the initial pressure is 1.25 atmospheres, and that's when we have 4 moles of gas present, the 4 moles of reactants that we have. What's the pressure at the end when we only have 2 moles? So what we're really asking here is just a relationship between pressure and number of moles, which we've already sort of covered today. So if we start with PV equals nRT, in this chemical reaction here, we're telling you that temperature and volume are constant, so we can move those over to one side. And pressure and number of moles is what's going to be changing. So it's going to be pressure divided by number of moles is RT divided by V, and those are all constant. So that same relationship we used in a previous problem is going to apply here as well. P1 over N1 equals P2 over N2. The only difference here is that we're doing a chemical reaction, so we're changing the identities of the gases, but as we said, the ideal gas equation doesn't care what gas you have. So at the beginning of the reaction, we have a mixture of N2 and F2. That's going to give us our initial pressure P1. And then at the end, we have NF3. So to sort of write that out in more detail, N2 is going to be the moles of product that we have at the end of the reaction. And N1 is going to be the moles of reactant. Now, we didn't tell you exactly how many moles we have, we just tell you the ratio, but we can assume any amount we want as long as the ratio is the same 1 to 3. So then what this means is, from the coefficients in the chemical equation, the ratio N2 over N1, well, let's do this first. Let's rearrange this first. We're going to solve for P2, which is going to be P1 times N2 over N1. And so when we put those numbers in, the initial pressure was 1.25 atmospheres. That's the pressure when we have our 4 moles of reactant gases present. And then N2 is the moles of product, which is going to be, in a relative sense, 2 moles from the coefficients. N1 is the moles of reactant, which is, in a relative sense, 4 moles. And so those are the 2 numbers we put in. All right, so we're forming 2 moles of gas from a mixture that involves 4 moles, and so the pressure will drop during that process. And so that comes out to 0.625 atmospheres. So the pressure is cut in half because the number of moles of gas is cut in half. So this is just the same relationship we used earlier in the class, just showing you that it applies to different situations, and even in the context of gas stoichiometry it works, because we don't care that the identity of the gases are changing. All we care about is how much we have at the beginning of the reaction, that's the initial number of moles we had, how many moles we have at the end after they react with each other, that's our final number of moles. And so any relationship that involves numbers of moles changing in some process, we can use that same relationship in this context here. So that one actually didn't really require us to talk about stoichiometry too much. We just had to use the idea that because of the coefficients being 1, 3, and 2, if we start with a mixture that's 1 to 3 ratio, total of 4 moles, at the end we would have then, in a relative sense, 2 moles because of the coefficients. So any questions on that one? All right, the next one we're going to do is more involved and drawn out. So it's going to require us to sort of illustrate. So first of all, how do we study reactions between two gases? How do we measure them out? How do we combine them and stuff like this? So one apparatus you can do that in is sort of shown here, where we'd have 2 glass bulbs represented as A and B, and they would have a valve in between C, which is in the technical term for that is a stopcock. And come on, don't laugh. So I heard that. All right, so you have two bulbs, A and B, of individual gases, and then you have a valve in between that sort of isolates them. So initially we're separating the 2 gases because the valve is closed, and we can measure out the volume of each of these and the pressure and all that stuff individually. And then when we open the valve C, that allows the gases to mix together. Because remember, the gases occupy the full space available to them. So if we open this valve up and allow the two gases are going to diffuse and mix, and they're going to now occupy the whole volume of the apparatus. That's kind of what we're doing here, how we would carry out a gas phase reaction. So let's say we're doing this reaction at 400 Kelvin, so we're taking phosphine gas pH3, which is in bulb A, reacting with oxygen gas, which is in bulb B, and they're going to form diphosphorus pentoxide as a solid, and then water vapor as a gas. So we're going to use the ideal gas law in the context of stoichiometry here. So bulb A is 12.5 liters. That's what we're telling you in the problem. So A, 12.5 liter bulb, that's A, is filled with 2 atmospheres of pH3. So the pressure in that bulb at the beginning of the reaction is 2.0 atmospheres. So remember, initially the 2 are isolated from each other. There's a closed valve here that sort of blocks the 2 from each other. So that's what we have in A, 12.5 liters at 2 atmospheres, and then B, we have 10 liters as the volume, and the pressure is 3 atmospheres. So that's the pressure and volume of each of those individual bulbs before they're mixed together, and again, they're initially closed off. So the first question here is how many moles of each gas are present at the start of the reaction? So that's what we're going to use PV equals nRT to figure out how many moles of pH3 and how many moles of O2 we have. So for both gases individually, the number of moles is just going to be PV over RT. We're just rearranging PV equals nRT and solving for N. Okay? So we can do that for both gases. For pH3, which is in bulb A, we have 2 atmospheres is the pressure. So here the pressures were given directly in atmospheres, so we don't need to convert them. The volume of bulb A, which is what contains the pH3, is 12.5 liters. And then RT, we have to use the correct value for universal gas constant, 0.0821. And then the temperature we're telling you is 400 Kelvin. And that's going to be the same for both. They're both at the same temperature. So what we get for moles of pH3 is 0.761. And then what we're going to do for O2 is the exact same thing, but make sure we're using the right quantities for that. So the oxygen, which is in the second bulb B over here, the pressure for that was 3 atmospheres. So we charge that up with a higher pressure, but the volume is smaller, 10.0 liters. And we have the same universal gas constant, same temperature for the 2. So R is always the same, it doesn't change for anything. And then temperature is still 400 Kelvin. So that comes out to 0.914. All right, so then that's going to be the moles of each gas to start with, and now from here the next part just becomes a stoichiometry problem. So what we're going to do now is we're going to open up the valve C here, and we're going to allow the two gases to mix together. So they're going to diffuse through the opening, mix together with each other, all that. And so the question B now, the second part of this problem is, once they're allowed to mix together, which gas is a limiting reactant? Now for that, we don't even need to worry about ideal gas law, because in the previous problem, we just figured out how many moles of gas we have. We have the balanced equation, so finding a limiting reactant becomes very straightforward. So what we had found is that for pH 3, we have 0.761 moles. And for O2, we have 0.914 moles. And we can't forget everything we learned in the past, because if we want to find limiting reactant, we just have to calculate stoichiometric ratios, is one way to do that. So for pH 3, we divide that number 0.761, number of moles, divided by the coefficient, which is 2. So to 2 digits, that comes out to 0.38. And then for O2, we take its number of moles, 0.914, and divide by its coefficient, which is 4, which is 0.23. All right, so this number is smaller for O2, so that means O2 is the limiting reactant. Now, we talked earlier in the class about chemistry not necessarily representing reality. This is actually an exceptionally stupid way to carry out this experiment, because you're using, so pH 3, I may have mentioned this before, pH 3 is like a horribly poisonous substance. I mean, if anyone asks you to do anything with pH 3, I would just recommend running and hiding and not listening to them. But anyway, pH 3 is horribly poisoning, but you're using the less poisonous gas as your limiting reactant. That means you're going to have your poisonous gas is going to be left over at the end. That's a really dumb way to do this reaction, because you're not letting all the really horrible stuff react. But anyway, that's what we find out, is that O2 is limiting reactant in this case. And then once we know that, we can still continue the stoichiometry problem and figure out how many grams of this product are formed. All right, so if we want to figure out how many grams of P2O5 are formed, we just have to do a stoichiometry problem. So at this point, it doesn't matter that it's a gas anymore. We have the number of moles of our limiting reactant, which is 0.914 moles of O2. And now we can just go through and do stoichiometry to figure out what this problem is asking. So once we have moles of limiting reactant, we can figure out moles of product by using mole ratios. So the coefficient for P2O5 is 1, and the coefficient for O2 is 4. So that's how many moles of our product P2O5 form. And then to find the mass of that, we just multiply by the molar mass. 141.94, that was given to us here. That's grams of P2O5 in 1 mole of P2O5. All right, so again, just a stoichiometry problem at this point. We get 32.4 grams of that product. All right, so even though we measured the two reactants in terms of their pressure and volume because they're gases, once we mix them together, a solid forms, and we can still calculate the mass of that solid using stoichiometry once we know the moles of each of the gas phase reactants. All right, so any questions so far? That's just mainly a review of chapter 5. All right, and then the next part of this is, that's where I stopped there. Okay, so that's where we're going to stop there. Now, in principle, what we can do is, you know, we could take this a step further, and if I had more time, I would. We could figure out now, okay, well, you know, we could figure out, you know, how much of the excess reactant is left over. We could figure out how much of the other product, which is a gas, is formed, and then at the end we could figure out what's the pressure at the end, because now we have, you know, this much gas that formed, this much gas that's left over, however much is left over, they occupy now the combined volume. So there's more things we could do with this, but we're going to stop there because I don't think our homework questions are going to go into that level of detail. But we should now know how to use PV equals nRT in combination with the stoichiometry concepts that we covered back in chapter 5. All right, so any questions on that problem there? All right, the next thing we're going to cover, which I think is the last major thing we're going to cover today, is called Dalton's law of partial pressures. So Dalton's law of partial pressures just deals with a situation where we're mixing two gases together. So again, what's the total pressure if we mix two gases together? That's really what it revolves around. So let's do a little bit of a thought experiment first. So let's say we have a flask that has 1 atmosphere of nitrogen in it, and then we pump in an additional 1 atmosphere of nitrogen. What do we think is going to be the total pressure? It's going to be 1 atmosphere, 2 atmospheres, 0, or who cares? So someone said 0. I don't know if they're trolling me or if they really think that, but So if you have one atmosphere and you add another atmosphere, what do you think the pressure will be? Right, they are. It should make sense to us that they are additive. So 2 atmospheres would be the case. If you start with 1 atmosphere and just add in another atmosphere, they do add together. So pressures are additive. So that's one sort of important backdrop of this Dalton's law. So if we mix 2 gases together and we know the pressures of the 2 gases we're mixing, the total pressure will just be the sum of those. Now that was true if it was the same gas, nitrogen mixed with nitrogen. What about if it's 2 different gases? So let's say we have 1 atmosphere of nitrogen, but this time we're adding O2, 2 atmospheres of O2 in this case. So if we add a different gas to the first one, do we think the pressures are still additive, or is it something else? So which of these A, B, C, or D do you think is going to be the final pressure if we take 1 atmosphere of nitrogen and add 2 atmospheres of O2? Someone said C. Yep, still 3. So it doesn't matter that we're mixing 2 different gases, the pressures are still additive. And that's because when we mix gases together, they mix homogeneously. Again, the ideal gas equation doesn't care what gas we're talking about. So similarly, the property of an ideal gas, which states that their pressures are additive, which we kind of intuitively figured out at the beginning, that's also going to be true whether it's 2 of the same gas we're mixing together or 2 or more different gases. So any mixture of gases, the gases combine homogeneously. And what that sort of means then is that each gas in a mixture sort of behaves as if it's the only gas present. So gases don't really care when they're mixed with anything else. That doesn't change their properties individually or change how they behave. They just sort of go about their business as if they're the only ones there, kind of like Houston drivers. All right, so each gas in a mixture behaves as if it were the only gas present. Just like each driver on the freeway behaves as if they're the only driver present. All right, and so that's how it works when you mix gases together. They're unaffected by the other gases being there. And so the pressures are additive and so on. And so that leads us then to a more sort of, specific formulation of Dalton's law of partial pressure, which has a few equations associated with it. So again, this law deals with a mixture of 2 or more gases. And so what are some of the equations then that come out of this? Well, the first is we just said that the pressures are additive. So if you know the pressures of all the individual gases that are mixed together, the total pressure is just the sum of those. So if we're mixing together gases A, B, C, however many we have, the total pressure is just the pressure of gas A plus the pressure of gas B plus the pressure of gas C, and so on. All right, where we call these PA, PB, PC, these individual pressures, however many gases we have, are called the partial pressures. All right, so when you have a mixture of gases, you can define a partial pressure for each gas, and then the total pressure is just the sum of all the partial pressures for whatever gases are mixed together. Now, sometimes a more useful form of Dalton's law is in terms of number of moles of each gas that we have present, and that just relies on PV equals nRT. So for each gas, the partial pressure is going to be nRT over V. So we can just rewrite this relationship up here in terms of number of moles. The total pressure is equal to the number of moles of A times RT over V plus the number of moles of B times RT over V plus the number of moles of C times RT over V, and so on, however many gases we're mixing. And when you mix gases together, they always are going to equilibrate to the same temperature, and they're going to occupy the same volume when they're mixed together, because remember, gases fill up the entire volume that's available to them. So what you can do is you can factor this out, and you can say that this is really equal to the total number of moles times RT over V. So again, in a mixture of gases, we don't care what the gases are. And for the total pressure, we don't even really care how many of each we have. If we're just trying to find the total pressure, we just need the total number of moles of gas. We multiply that by RT over V. So it doesn't matter. Ideal gas equation still applies, whether it's a single gas or a mixture of 2 or more gases. And that's what this says here. And then finally, the last form of this equation that's going to be sometimes useful is in terms of what is called the mole fraction. So this is a new quantity we haven't seen yet. But if we want to find the individual pressure in a mixture. So let's say we have a mixture of gases and we know the total pressure and we want to find what's the partial pressure of one of those gases. That's going to be given as the mole fraction, which is abbreviated as chi, for that gas times the total pressure. So mole fraction is a ratio of the number of moles of that gas we have divided by the total number of moles of gas that we have. All right, and that's again called mole fraction. So we dealt with mass fractions earlier in the course, and this is just a related one called mole fraction. When you have a mixture of multiple gases, the mole fraction for any gas in that mixture is the moles of that gas divided by the total number of moles in the mixture. All right, and again, the way this works, to convince ourselves that this is true, let's think back to this equation up here. So if the partial pressure for each gas is the mole fraction times the total pressure, that means that that equation above that we first started with would be rewritten in this way. So we can rewrite it as the mole fraction of gas A times the total pressure plus the mole fraction of gas B times the total pressure plus the mole fraction of gas C times the total pressure, and so on, which is equal to chi A plus chi B plus chi C times the total pressure. The sum of all the mole fractions is going to be equal to 1, and so that just sort of proves that this is valid, because again, total pressure equals total pressure, so that's what it comes out to. So this kind of hopefully convinces us that we can use this relationship for each of these partial pressures as well. So there are different ways you'll do it, but they're all related to the idea that when you have a mixture of gases, the total pressure is just determined by the total number of moles of gas you have, and each gas has its own partial pressure, which, as this equation states, is related to the mole fraction of that gas in the mixture. So we can think about it in either of those contexts. All right, so those are the equations for Dalton's law. Now let's see a couple ways that we use them. So here is, we have a mixture of two gases. So we have 40 grams of oxygen and 40 grams of helium with a total pressure of 0.9 atmospheres. What is the partial pressure of O2? So here we're going to use Dalton's law to calculate the partial pressure for one of the gases. Now it might be tempting to say, oh, we have equal amounts of both gases, 40 grams of O2, 40 grams of helium. That means their partial pressures have to be equal, so they're both 0.45. But that again is not quite the right way to think about it, because these relationships are in terms of the number of moles of gas, not the mass of each gas that you have. So what we just introduced is that the partial pressure for a gas, we're looking for O2 here, is equal to the mole fraction, not the mass fraction, times the total pressure. So what we have to do for this problem is we have to calculate the mole fraction of O2 and then multiply that by the total pressure, which is given to us here as 0.9 atmospheres. All right, so we already have that number. We just have to calculate the mole fraction. So remember, the definition of mole fraction is going to be the moles of that gas, in this case O2, divided by the total number of moles. In this mixture, we just have O2 and helium, so it's just going to be the moles of oxygen divided by the sum of those two, oxygen plus helium. All right, so we just have to calculate the moles of each gas. Well, we know how to do that because we have the masses of each of them. So the moles of O2, we have 40 grams. One mole of oxygen has a mass of 32 grams, so that's the molar mass of O2, 2 times 16. So we have 1.25 moles of O2. And then for helium, the atomic mass is 4 from the periodic table, 4.00. So 40 grams would be 10 moles in this case for helium. So a lot more moles of helium in this mixture, even though the mass is the same. All right, so we're just using mass to mole calculations to figure out the moles of each, and now we can calculate the mole fraction by taking the ratio. Moles of O2, which is 1.25, divided by the sum of the two, 1.25 moles of O2 plus 10 moles for helium. So that ratio comes out to 0.111. All right, so mole fractions are unitless quantities because they're ratios. So that's the fraction of O2 in the mixture in terms of moles. And so we're just going to take that number, 0.111, and multiply it by the total pressure of 0.900 atmospheres to figure out the partial pressure of O2, which is going to be 0.0999 atmospheres. All right, so even though we have equal masses of the two gases, it turns out most of the pressure comes from the helium, not from the oxygen. We see that the partial pressure for O2 is, only about 11% of that value. Now, why that is, we have the same masses for both gases. Why don't they have the same pressure? Well, that's going to make more sense after we talk about what we're talking about in the next class about how the properties of the molecules determine some of these macroscopic things like pressure. But that's the math that comes out using just Dalton's law. We get 0.0999 atmospheres. So that's how we would calculate partial pressure when we have a mixture of gases where we know the amount of each gas and we know the total pressure. We can back out partial pressure of either of them. It's also important to recognize that the sum of the partial pressures will equal the total pressure. So if we want to get the partial pressure for helium, we just have to subtract the two now, and that would give us the pressure of the other gas in the mixture. All right, any questions on that? All right. The last application of Dalton's law we're going to talk about is another thing related to stoichiometry. So we're getting close to the end of our stoichiometry party in this class. We're not quite there yet. And this is an application of Dalton's law. So first let's describe the experiment that we're doing here. Again, this is kind of primitive. You might do something like this in the lab. I'm not sure. It's a feasible experiment. It's not the most high-tech way of doing it. But what this experiment allows you to do is it allows you to measure and quantify products that are formed as a gas during a reaction. So here's an example here. If we take, we're taking two ionic compounds mixing together, KClO3 and MnO3, and we heat them up together, and this will release a gas as a product. I believe it's going to be Cl2 or probably O2, sorry. O2 is going to be released as a product. So we don't have the exact details yet, but what you do is you're taking a reaction where the reactants are solids and or liquids, and then you're heating them up, and one or more of the products that's produced is a gas, and so the gas is released. Now, if you guys have done chemical reactions in the lab before, for those of you that are far enough along in that, you know that one of the things you do when you run a chemical reaction is you want to measure the product and calculate percent yield and all that stuff, just like we talked about in here theoretically. But it's hard to do if your product's a gas, right? Because if you just heat up a gas, if you just heat up a reaction in open air and one of the products is a gas, it's going to go everywhere. How do you collect that gas? How do you measure it? And so on. So this is an apparatus that allows you to do that. So let's describe it first, and then we can see how we do problems involving it. So first what we have is, again, we're doing a reaction here that produces a gas. It works best if it's only producing one gas, because then we know exactly how much of that gas we'll have. If it's a mixture of two gases, we can still work with that, but it's not as convenient, obviously. So it produces a gas, and then what happens is the gas is sort of transported over here. So the gas is formed here, and again, gases are going to fill all available volume. So the gas is going to be transported over here to the collector. And that just happens passively. There's nothing we have to do to force that to happen. That's just how gases behave. They just diffuse and they take up all the available volume. We'll talk more about diffusion next time, but we're going to just, all the gases are going to diffuse into this collector here. And the way the collector is set up is that it's basically a jar, or in more practical sense, like a graduated cylinder, something that has a volume measure on it that's inverted into a dish of water. So then what happens is that the gas is going to bubble up here into the top of this collector, and it's going to push down, it's going to displace some of the water that's initially present inside of that collector. So the gas displaces water in the collector. That's what we're showing here in number 3. All right, so it displaces water, and so as that happens, then the surface of the liquid drops because gas is pushing down and displacing it, and basically then we can measure the volume of the gas that forms based on the change in the volume of the liquid level as it goes down. So if you have a graduated cylinder that's inverted, and you can just measure how much that liquid level drops during the reaction. That'll tell you the volume of the gas that was produced that's displacing that same volume of water. All right. Now what we have to do when we account for this though, so we can measure the volume directly, but then we have to understand is that what is going to be present in this area up here above the liquid is going to be really two things. We have to account for not only the gas that's present that's coming from the reaction that's displacing the water, but also there's going to be a little bit of water vapor that's present above here as well. So if we're going to do this accurately, we have to account for the vapor pressure of water. And again, vapor pressure is a topic that we're going to cover in more detail in chapter 9. So by the time the exam rolls around, you'll have a much more clear picture of this. But basically, vapor pressure is the idea that whenever you have a liquid, at the surface of the liquid, there's going to be some percentage of molecules of that liquid that are able to escape into the gas phase. And that's what we would call humidity, for example. If you're, or if you're in a regular day in Houston, there's water vapor in the air that we call humidity, but basically anytime you have water present, some amount of that water is going to evaporate from the surface and you're going to have water molecules that are in the gas phase above it. So above this liquid here, in this what we call head space, this volume of gas that's above the liquid, we're not only going to have the gas that's being produced during the reaction, but we're going to have a little bit of water vapor as well that comes from the surface of the water that's right below it. So some portion of water molecules escape into the gas phase, even though water is normally a liquid at room temperature, but some small portion escape into the gas phase. They escape the surface, and they create a small partial pressure. And so this is where Dalton's law comes into play, because the gas that we're measuring up here, it's not just the gas that we're producing in the reaction, but it's the gas we're producing in the reaction plus the water vapor that's above it. So it's a mixture of two gases in reality. Now the vapor pressure of the water, what that partial pressure is for the water vapor is temperature dependent. So it depends on what temperature you're collecting at. We'd have to really tell you that value. There's no way of calculating it, or it's not a constant necessarily. Do they really have to do like the most loud maintenance work during their class every week? My gosh. So that's what's going to happen. We're collecting the gas over here, and this gas that we're collecting is a mixture of the gas that's produced by the reaction and the water vapor that's already present. So let's just see how this works then in an example problem. So acetylene, which is C2H2, you've probably heard of acetylene torches. That can be, one way to produce that is to take calcium carbide. So this is an ionic compound we haven't really talked about, but carbide is like a carbon anion. So it's CaC2. It's really a C2 minus anion. And you can add it to water. So if you mix calcium carbide with water, you're going to produce acetylene C2H2 as a gas, and then you can collect it in that apparatus that I just described. So if we collect acetylene over water, we find if the total pressure is 738 torr and the volume is 523 milliliters, so again, we're collecting that gas sample, and we're measuring that the volume of the gas is 523 milliliters, and the pressure was measured separately as 738. That's the barometric pressure in the room. If the vapor pressure is 21 torr at this temperature, how many grams of acetylene are produced? So again, in this type of problem here, we're going to use Dalton's law of partial pressure and the ideal gas equation to figure out how much of our gaseous product is produced when we collect it in this way. So we're not able to directly measure the mass of a gas very easily, but we can collect it, measure its volume and pressure, and use the ideal gas equation to do that. So the key idea here is to remember that when we're collecting a gas in this way, the total pressure is equal to the pressure of the gas we're collecting, which is C2H2, plus the water vapor pressure. Again, that's why we give you this number here for the vapor pressure of water, because that total pressure is going to be the sum of the gas you're collecting in water vapor. Now, water vapor pressure is not particularly high at room temperature, so it's not going to be a huge correction, but your answer will be a little bit off if you don't account for that. So then what we can do is we can just use subtraction to find the partial pressure of the gas we're collecting, C2H2. So it's going to be just the total pressure minus the water vapor pressure. So our total pressure, we're told, is 738 torr, and the water vapor pressure is 21 torr. So that means the pressure of the gas that we're collecting itself, the partial pressure for that gas, is 717. All right, so the common mistake that people make in this problem is they just take the total pressure, 738, and just start going to town with that using the ideal gas equation. But we have to account for the fact that some of that total pressure is from the water vapor, and so only this part of it, 717, comes from the gas that we're collecting, because that's what we're trying to measure here. So then from there, once we know the pressure of the gas, we have its volume, we have its temperature, so we should immediately think of ideal gas law to figure out how many moles of that gas we collected. So now we can find the number of moles of the collected gas, C2H2, by using the ideal gas equation. The partial pressure of that gas times the volume divided by RT. And so now we can start plugging in the numbers that we have. The pressure was measured in torr, so we have to convert that to atmospheres before we use the ideal gas equation, because we are using R as part of that calculation. So we have to divide that by 760. So that comes out to 0.943 atmospheres in the correct unit. The volume we're told is 523 milliliters. That needs to be in liters for the ideal gas equation, so 0.523 if we divide by 1,000. Oh, I think my tablet, come on, really? My thing froze. Let me check. Probably not going to come back. Let's see. Is it just the pen? No, it's not the pen. All right, well, since we're close to the end, I think that's the last thing, right? Well, okay, there's two more things to do. I don't want to have to splice the video and deal with that today. So let me just talk you through the rest of this, and then I'll put it in the notes so you can check the work that I did. So basically what we're going to do for the rest of this problem is we're going to finish putting everything into PV equals nRT. So we have the pressure and the volume, RT in the bottom. That's going to give us the number of moles of the gas that we collected using PV equals nRT. Now we're looking for the mass. So the next step after that is going to be, which I gave you some more space to do, once we find the number of moles, we just multiply that by the molar mass to get the mass of the gas that we collected. So again, we're not able to directly measure that mass, but we calculate the number of moles, and then we use molar mass to get that. So that's going to be the next step there, which you should all know how to do because that's just stoichiometry. And then the last step here, which I'll also put in the notes, but I don't want to reset my tablet and work through it separately, is that if we assume 100% yield, how many grams of our starting material, our reactant CaC2, did we need to produce this? And then again, that's just a stoichiometry problem. So we figure out how many moles of that substance we collected up here. If we're making that many moles of product, we have a balanced equation, which is 1-to-1 in terms of CaC2 and that product. So we use stoichiometry to figure out the moles of calcium carbide that we needed to produce that, and then we use its molar mass, given here 64.1, to figure out how many grams of that was required. So I'm not going to go through those because I don't want to waste the time of resetting, but hopefully that makes sense because the rest of this is just stoichiometry at this point. So the only really new thing was, again, to account for the partial pressure of the water vapor, subtract it out, and then from there, ideal gas equation to find number of moles. All right, so I'll have that completed for you before I post this, but if you have any questions, let me know. Definitely try out the rest of this on your own if you have time, and I'll see you guys next week, and hopefully the tablet will make it all the way through class that time.
Will you be at like Thursday?
Thursday, yeah, sorry, still the same week.